because there is no way I'm making it on a Reaper. So I'd rather destroy it for good.
Oh, you got the wrong machine. Hooked up to the wrong
well, it's better
port.
Let's
try
that's
two.
the one ring.
The one ring.
That looks good. Okay. It looks like the usual stuff.
One ring with the eye.
I thought it was a ring and a glazed donut.
It's actually the one ring and the eye. I have Sauron.
No, I'm gonna go with glazed donut and
Yeah, that is the Eye of Sauron and the ring.
Well, yeah, it is. It is the Eye of Sauron with the ring.
Yes. But so far, I have not been accused as a Satan worshipper, so that's good. All right, so let's go ahead and get started today. We are going to have a lab activity tonight that will kind of get you closer to the 3x3 carry look ahead adder. So that's going to be the focus of the evening activity after the lecture. So what we'll do today in class is to talk about subtraction. Okay. Are there any questions about carry look ahead addition at this point? Is everybody comfortable with addition? Okay, and everybody knows what those terms are? X, Y are the input, Q is the intermediate sum, K is the carry, and then S is the sum, the actual answer. Yes? Okay. All right. So in that case, I'm going to start with binary number subtraction. And as with the addition, I'm going to start with base 10 subtraction first. Okay? In other words, I'm just going to review the concepts in subtraction. And you go like, but I learned that a long, long time ago. We don't need to be reminded of that, right? But some of the concepts may actually be useful to get a quick review. Okay, so we're going to go do a quick review of those concepts. And let me hook up my tablet first. Okay, it might be here already somewhere. Nope. Nope, that's just my... Oh, there we go. It's just a little bit slow. There we go. Click OK. So we'll talk about subtraction a little bit in base 10, just so that we are familiar with the concept of a borrow. Okay? All right.
Did you start recording?
Yeah, it should be recording already. But I left my I left my stylus in the other classroom. It's okay, I got another stylus, but this is not my preferred stylus. This is the one that comes with the tablet, but it has a button on it, and I always keep clicking the button unintentionally. So I'm gonna go back to the other classroom, to get my stylus, but not now. Okay. Yeah, so we'll go ahead and take a look at a subtraction, and let's see. See, I just clicked it. I have to put that button on the other side so I don't accidentally click it. All right, so we'll have a 5 minus. Oh, why is that not working? Okay, 5 minus 8. Okay. What is 5 minus 8? Negative 3 is 1, but if I want to be able to perform multi-digit subtraction, then how should I call the result of 5 minus 8?
Use the first digit as a plus or minus symbol?
Well, we can say this is 7 with a borrow of 1.
Oh.
Right? It's a subtraction, so if a digit does not have enough value for the subtraction, you borrow from the more significant digit. Does that make any sense? Okay, so here is the concept of a borrow. What is it? Okay, we do it mechanically, but what exactly is a borrow? I got $5 in my pocket. There's a bully waiting for me outside, wanting $8. Okay, I walk outside. The bully said, okay, do you want to lose $5 or do you want to get a black eye and go like, well, I don't want either, but I can try to get you $8. But then I only got $5 in my pocket, right? So I go to one of you and go like, well, do you have any money I can borrow? But you're the next digit, right? So 1 to you is 10 times what I have, 10 times my unit. So when I borrow quote unquote 1 from you, I'm actually borrowing a quantity of 10. Okay? So then it becomes 15 minus 8, right? So I give 8 to the bully, and I end up with 7 in my pocket. Is that making any sense? But no, it doesn't make any sense. Because I only started off with $5, now I have $7 in my pocket. So the idea is I owe $10. Okay? This borrow of 10 is not forgotten. I owe 10. So my net worth is whatever I have in my pocket minus what I owe. So that means it's 7 minus 10, which is negative 3, which turns out to be 5 minus 8. Is that okay? So the whole concept of a borrow has to do with when you need to do multi-digit subtraction, the borrow allows you to do multi-digit subtraction. Is that okay? So if the digit of the, I cannot remember which one, so let me look up those terms. One is minuend, the other one is subtrahend.
I think the first one's subtrahend.
The first one is subtrahend? Okay. So this one is subtrahend. I'm going to write it here. So subtrahend, and this is minuend, I think. Could be wrong in terms of spelling. So when the subtrahend digit is less than the minuend digit, then you need to borrow. Okay? And that's the whole idea of borrowing. And you might go like, okay, so this is the kind of stuff that you have memorized. But subtraction is particularly nasty because addition is commutative, which also means, if you can remember 7 plus 8 is 5 with a carry, then the other way around is the same. Because 7 plus 8 is the same thing as 8 plus 7. So the amount of stuff you need to memorize is only really 1/2 of the full table. Is that making any sense? But subtraction is not commutative, which means you cannot use that trick. 8 minus 5 is not the same thing as 5 minus 8. So that means subtraction is actually more difficult to learn from the perspective of a second grader or first grader, depending compared to addition. Is that okay? Do you guys remember that subtraction was harder to learn compared to addition? No? Okay. All right, so this is base 10. Okay, so the idea of using base 10 is really just to remind you of the concept, but not so much that we are going to deal with the binary subtraction using those particular rules. Yep.
Was that word
Minuend is the second number, is the amount that you are subtracting from. I spelled it as minuend, but I could be wrong, so I'm going to double check that. Subtrahend and minuend. Okay, so let me zoom. So okay, so I got it flipped. It's okay. We'll fix that. So minuend is the first number, and then subtrahend is the other one. I'll switch back to the tablet once I fix this. Okay. There we go. So this one is fixed, and it should be correct. Is that okay? All right. Okay. So now we want to deal with base 2. Okay. So base 2 is supposedly a lot easier to deal with compared to base 10, right? Okay, so let's go ahead and deal with base 2. So in base 2, we have, okay, let's do all the hard ones first. Okay, 0 minus 0 in base 2. What do you think is the result?
0.
The result is a 0. What about the borrow?
0?
You have to borrow. The borrow is a 0 as well. Okay, so we'll call it a borrow of 0. Okay? Okay, we'll try another really hard one. 1 minus 1. What is the result of 1 minus 1?
0.
Are you sure this is base 2? Okay, I'm just pulling your legs. Do we have any borrow?
No.
No. Okay. And another hard one. 1 minus 0 is 1. Okay, the result is 1, and then the borrow is 0. So that leaves us the easiest one. 0 minus 1. And what is the result?
2.
No, the result, no. Okay, the result is 1, because after you borrow a 1, then you have a quantity of 2. The quantity of 2 minus 1 is 1. Is that okay? That's it. That's all you need to remember in base 2 subtraction. Yep.
Do you mind writing that part out?
Say that one more time.
That part, the carrying from the base 2 part, on the 0 minus 1.
0 minus 1 is 1 as a result, and it also has a borrow of 1. Okay, so the last column, B, is for indicating the borrows. Did I think it's going a little bit.
Wanted you to like show the borrow, like how you did with the.
Yeah, like with the first one.
Oh, okay.
Yeah, basically.
I'm sorry, I totally lost you there. That's why.
Vertical column, okay. Sure, absolutely. So, do you want to do it for all of them or just one? Just the last one? Okay, so we got 0 minus 1. Okay, but these are in base 2, so that's important. So regardless of the base, 0 is less than 1. So we have the minuend, which is 0, being less than the subtrahend, which is 1, which also means, oh, I need to borrow from the next digit, right? But when I borrow from the next digit, even though I'm quote-unquote borrowing 1 from the next digit, the quantity the next digit is representing is twice of what I'm representing. So when I borrow 1 from the next digit, I'm actually borrowing the quantity of 2. All right? So now it really becomes 2 minus 1, and 2 minus 1 is 1. That's why the result is 1 with a borrow of 1. It is no different from 0 minus 5 in base 10 is 5 with a borrow of 1. Is that okay or not? The most important part is when we borrow from the next digit, what is the quantity that we are actually borrowing? That is the base. In base 2, when you borrow from the next digit, you're borrowing the quantity of 2. In base 10, when you borrow 1 from the next digit, you're borrowing the quantity of 10. So that whatever you borrow is combined with what you already have as the minuend, and that quantity, so you're subtracting from that sum, which is the borrowed amount plus whatever you have. Yep, go
So
ahead.
if it was 0 base 3 minus 1 base 3, the answer would be 2.
0 minus 1 in base 3 is 2 with a borrow of 1. That is correct.
Okay. That makes sense.
Which is just like 0 minus 1 in base 10 is 9 with a borrow of 1.
Alright, thank you.
So are we okay so far with that concept? Okay, cool. So the next thing we want to do is I'm going to go back to the table. The table is nice in a way because it looks kind of like a truth table already. Okay, so when you look at this, it looks like a truth table because this is x. So x is our minuend. I clicked again. So this is x, which is the x is the minuend, and then y is our subtrahend. Okay, so once again we are looking at this as a truth table. It's not very convenient right now, but we can at least tell something from here. When you look at the R column, what do you think? How is R related to x and y? If I want to look at it from the perspective of logic gates, exclusive OR. Yep. Haven't we seen that before? Exactly. Well, not just the carry look ahead, but for binary addition. So the result of subtraction is identical to the result of addition. There's no difference between those two. But something has to be different, right? Because otherwise subtraction and addition would be exactly the same thing. So something has to be different. What is different? The borrow is different. Okay? When you look at carry, the one time we have a carry of 1 is when we have 1 plus 1. Then we have a carry of 1. But when we are talking about subtraction, the borrow is a 1 if and only if x is 0 and y is 1. That's the only difference between addition and subtraction. Is that okay? All right? So what that is inspiring me to do is to say, if I look at r as a function, okay? If I look at r as a function with 2 bits, so we are subtracting y from x in this case, but from the perspective of a logic gate, it makes no difference. It is still x exclusive or with y, which is identical to the definition of the r function for addition. It's the same. The only difference is b. Okay, so when we look at the borrow, when we subtract y from x, then we have to say, okay, so how do we use a logical expression so that when x is 0 and y is 1, then we want the borrow function to be a 1? Well, we can use an AND, okay? But not just an AND, we need to negate x first. So when you look at this, if I negate x is 0, the negation of 0 is 1, okay? And then I do conjunction with y, non-negated. Then we have 1 and 1, which makes the result 1. That is our ticket to define b as a function. It would be the negation of x conjunction with y. Question?
No.
Okay. So is that okay? All right. But the profound part of this part of the discussion is, even though the table itself, your x, y, r, b, that table is from the arithmetic perspective, the function that we're defining, r and b, are using only logical operators. Which means by using logic gates, now we have a way to implement subtraction, at least a simple subtraction. Is that okay? All right. So the next thing we're going to do is to look at an actual subtraction in binary. So we exercise all of these things. All right. So we'll scroll up a little bit more, and then we use an actual subtraction. So we'll go 0, 1, 1, 0, 1, 0, 1, 1 in base 2, and then we put a 0 here. This row is x, which is the minnow end. This row is y, which is the subtrahend. This row is q, which is the same thing as q in addition. In addition, we call it the partial sum. In subtraction, we call it the partial difference. Okay. This is t, which stands for the borrow. I cannot remember why I chose the letter t, but that's how I use it in the notes. And then the last row, I just call it d for difference. Okay. All right. So how do we do this? Well, let's start from the column. Let's start with the rightmost column, because that's how we usually do things. So we got 0 minus 1 over here. 0 minus 1, if you look at the table, the result is a 1. So we put a 1 here. The borrow is 1 as well. Okay, so we put a 1 here as our borrow. Is that okay? So it is not really that different from base 10 subtraction, except I really spell out the second subtraction, whereas most of you do not spell out the subtraction of the borrow in a normal subtraction. The reason why I spell out the second subtraction is because when we build a circuit, we have to make it explicit. So that's why I have to spell out every single operation when I try to explain this, and then later on turn it into logic gates. Okay, so now we look at this 1 minus this 0, which is this is the 0th bit of the borrows, and we assume it to be 0, okay? Because this is a stand-alone calculation, so we assume that it's 0. 1 minus 0 is a 1. Okay, so we're done with the least significant column. Now we move on to the second least significant column. 1 minus 1 is a 0. Okay, so we put a 0 here. And 0 minus 1 is a 1, but also with a borrow. Okay? And then we look at this column here. 1 minus 0 is a 1. And then 1 minus 1 is a 0. And because neither subtraction contributes a 1 to the borrow of the next digit, the borrow of the next digit is going to be a 0. So we put a 0 here. And then we got 0 minus 1 is a 1 with a borrow. And then 1 minus 0 is a 1. So that finishes the whole calculation. But the question is, does it make sense? Okay, is this what it is supposed to be? So we can always do the same calculation in base 10 and see if it makes sense. We look at 0, 1, 1, 0, which is representing 6 in base 10. We look at 1, 0, 1, 1, which represents 11 in base 10. And then we perform this subtraction. And of course, when you do this subtraction, the answer is negative 5. Then you go like, oh, hold on a second here. That negative 5 and the 1, 0, 1, 1, they don't match up, right? But hold on a second here. Negative 5 is only one way to represent the quantity of negative 5. I could have said, I could have said it is a, let's see, 6 minus 1 is it's a 5 with a borrow of 10. Okay, yep.
How are you borrowing from the last digit when there's nothing to borrow from?
You just owe. You just owe that much.
Oh, okay.
Yep. Okay, so we know that the 1, 0, 1, 1 represents the quantity of 11. Okay, because it's 1 plus 2 plus 0 plus 8. 8 plus 2 plus 1 is 11. Okay, so that's why 1, 0, 1, 1 as a binary number represents what we know as 11 in base 10. Yep.
1 minus 1, it's 0 with the borrow 0, or is it borrow 1?
You mean this 1 minus 1 or this 1 minus 1?
The top 1 minus
1
1.
minus 1 is a 0.
Yeah.
0 minus 1 is a 1 with a borrow.
How about the last borrow that comes from the previous
Huh?
column?
The last borrow? This one?
No, from the top, so 0 minus 1 at the very left hand top.
This one?
Yes.
Yeah, 0 minus 1 is a 1 with a borrow. And then 1 minus 0 is just a 1.
Alright, so we don't do anything with that last borrow?
Well, let's find out.
Alright.
This is 6, this is 11. So this 11 is saying that, so we are basically saying 6 minus 11 is 11. But hold on a second here. We have a borrow, don't we?
Yeah.
What are we borrowing? 1, 2, 4, 8, 16. So we have $11 in our pocket, but we owe 16. So what is your net worth? Negative 5. Same as this one. Okay? Now, the base 10 one can also be treated the same way. So if you look at the base 10 one, and if we want to use, just borrow, and without using negative quantities, then you can say 6 minus 1 is 5 itself, right? Yes. Okay?
Right.
And then 0 minus 1 is what? 9 with a borrow, right? And that's it. So we end up with $95 in our pocket, but we owe 100. So our net worth is 95 minus 100, which is negative 5. So we end up at the same quantity, just represented differently. Is that okay?
So then after all that's said and done, then you do addition to add those all up and get that negative number, correct?
To get
What you have the negative 1, and then you'd add all the rest of them together.
Right, the quantity it is representing has to take that borrow into consideration.
Okay.
So you're basically saying, okay, I have $11 in my pocket, but I owe 16.
Okay.
So that owing 16 is important.
I'm just wondering, so it's automatic. I'm just trying to figure out how the logic gates recognize a negative number.
The logic gates don't care. The logic gates are, remember, what are the logic gates? Okay, we can boil all the logic gates down to the NAND 2 gates, right? A NAND 2 gate has 2 P transistors and 2 N transistors. The transistors don't care about positive nor negative. They're only saying, am I on, am I off? Okay? The gate only has to say, okay, is the output of this gate a 1 or a 0? Is it high voltage or low voltage? That's all it cares. So the question now is, how do we represent a negative quantity when that is the actual value that we want to represent? So we'll talk about it after we talk about subtraction.
Okay.
So right now our focus is just getting these zeros and ones worked out.
Okay, I gotcha.
But that's a good question. How do we represent negative quantities? Okay. All right. So now we can summarize, or we can generalize from this observation. So we start a new page, and then this time we look at the individual bits as x0, y0, x1, y1, and so on. So we are not now looking at individual bits. So we start with x0, okay, x1, x2, and if you want, x3, but I'm going to use 3 bits only. Then we have y0, y1, and y2. And here's my original subtraction. And then my second subtraction is going to have b. I used the other letter, sorry. So in the notes I use t. So this is t0, this is t1, this is t2, and then here we have q0, q1, q2, and then we have d0, d1, d2, and remember t3 is actually significant, so we have to keep track of that as well. So instead of using actual zeros and ones to carry out the calculation, now I'm saying, okay, we're going to use the variables. Each variable here is representing a single bit. So x as a minuend is a 3-bit number. Y as a subtrahend is a 3-bit number. But I'm spelling out every single bit as a variable. Is that okay? All right. So remember how we get to the q's. So if I just look at the qi, what is q subscript I? I being 0, 1, or 2. It is the result of subtracting yi from xi, right? Okay, so we'll write that first. Okay, the result of subtracting yi from xi. But what do we know about this from earlier? Can we do it with a single logic gate? Do you remember how our R was defined earlier?
It's exclusive OR.
Exclusive OR. Very good. Okay, so it is just xi exclusive OR yi. The plus with a circle around it means exclusive OR. Are we doing okay so far here? Are we associating what we talked about earlier to the generalization here? Okay, all right. Of course, another way to write this is, we talked about this in the previous class already. It is not xi, yi, or. This is a regular or because it doesn't have a circle around it. Xi, not yi. So it can also be expressed that way. This is all coming from addition. When we talk about addition, this is how we describe the R function. Can I help you guys?
Oh, we're just trying to figure it out. I'm confused still. I'm sorry.
No, that's fine. But which part do you want me to kind of go over?
Oh, I was just thinking of the problem earlier. We ended up with it's 6 minus 11, and when we ended up with 1011, which was supposed to be -5, but isn't that also
11? It is 11.
It is 11.
But we owe 16.
Oh. Okay.
So we have 11, but we owe 16. So the net worth is -5.
Okay. So I was right. That actually did it.
Yep. Okay, so we got the Q's. What about the D's? Okay, so let's deal with the D's first. Di is what? Well, Di is the result of subtracting D0 from T0, right? So how do we work this out? It's the same R. It's the result of subtracting T0 from D0. Oh, okay, I got it wrong. Okay, it's the result of subtracting, this is Q0 and T0, sorry. Okay, so D0, or the subscript I keep, okay, there we go, I. Okay, so DI, okay, pick any one, is the result of subtracting the T from the Q. Okay? So it's the result of subtracting the T from the Q, and they all have the index I. But we know what R is already, don't we? So we know how to express that in logic gates. So we know, oh, this one is easy too. So it is not QI or QI not TI. Okay, not a big deal. So once again, the tricky ones are the borrow bits. Okay, it's okay. It's just the PC falling asleep. So the tricky ones are the T's. Okay, T0 is given. That's an input pin. So let's figure out what is T1. Or what is TI in general? So there are two ways to contribute to a T, because the subtraction, okay, let's take just T1 into consideration. The subtraction of Y0 from X0 can contribute a 1 to this T1, but the subtraction of T0 from Q0 can also contribute to T1. Okay? So I will make this easier to write. So when we look at T subscript of I plus 1, then it has to do with the borrow of subtracting yi from xi, but it also has to do with the borrow of subtracting ti from qi. So now that we have two individual bits or two individual Boolean values, how do we combine these two to become t? Do you guys remember what I did in the actual example? They can both contribute, right? So if at least one of these two is a 1, then we have a borrow. So we use an OR. Exactly. So these are OR here. So when you express this, then it becomes not xi yi or not qi ti. Haven't we seen something like this, except the T's are called the K's, the D's are called the S's?
Yeah, it's just addition.
Yeah, with the only exception that these guys somehow end up with a little negation on the first term. That's the only difference. Does that make any sense?
Mm-hmm.
So at this point, we end up with the same problem that we had with addition, which means Ti plus 1 depends on Ti. Ti in return depends on I, Ti minus 1, Ti minus 1 depends on I, Ti minus 2, and so on. So we still rely on the rippling effect to go from right to left. So we want to use the same solution with carry look ahead. This time it's called borrow look ahead. Okay, but the question is, does the math work out so that we can use that technique? That becomes the next question. Yep.
Can you put in for xi not yi and then for qi not ti?
You mean here?
Or sorry, is borrow different?
Borrow is different.
Should we define borrow?
Yes, we defined borrow a little bit earlier. So we defined borrow from here. So we define borrow here. So are we okay with the math at this point?
Yeah.
Okay. All right. So now we end up with the same problem that we had earlier with addition, which means we are relying on the borrow to ripple through the subtractor in order for the last borrow bit or the most significant borrow bit to become effective. So now we look at this math again. Okay, so I know how much you guys like Boolean algebra, so we are going to do it again.
Love it.
Okay. All right. So Any questions about the first row? We just wrote it, right? I just hand wrote it on the tablet. The borrow of I plus 1 depends on the borrow of subtracting yi from xi or subtracting ti from qi. Okay, which is something that we just did earlier. From the first row to the second row, all I did is to expand the borrow function. Okay, the borrow function is the only difference between addition and subtraction. Because in addition, we have the carry function, which is a simple conjunction. The borrow function has to negate the minuend, but keep the subtrahend the same as what it is. Okay? So from this first row to the second row, it's just expanding b. What did I do with from the second row to the third row? From here to here. I expand qi, very good. What about from the third row to the fourth row? Yes?
I don't know if this would take way too much time, but for me it would definitely help if you just made up a table and then like started inputting the numbers in the Boolean algebra so we could like actually see how it's.
I can do that. Let me finish this first, and then I'll show you a really nifty way to do that. But we'll get this part done, and then we'll switch to a tool that will let you kind of visualize, how the calculations work out. Okay. So, but we'll do this first. All right. So, what did I do from here to here? We talked about that kind of really fancy, spancy Boolean transformation called. It starts with a D. De Morgan's law. Very good. So, De Morgan's law allows you to quote unquote distribute a negation into a conjunction or a disjunction. So in this case, I have a disjunction a negation on the outside, and we have a disjunction in the inside. So what I'm doing is I'm applying De Morgan's law to distribute this negation into the terms of the disjunction. But by doing that, I also have to change the disjunction operator into a conjunction operator. And that's why we end up with, we went from here to here. So this negation is applied to this term. It also applies to this term, and therefore there. But the disjunction is now turned into a conjunction, and because we use the multiplication, quote-unquote multiplication notation, so it's not represented. Okay, it's not displayed. Is that okay? All right. What about from here to here? What did I do?
Just simplified it.
Nope. We applied De Morgan's law again. We apply De Morgan's law again by distributing this negation to the terms of the conjunction, and the same thing over here, distributing this negation to the terms of the conjunction. Okay? So this term becomes just the negation of xi. This term becomes the negation of yi. Double negation cancels out. But we also change the conjunction to a disjunction, because De Morgan's law works in both directions. You can distribute the negation into a conjunction. You can also distribute a negation into a disjunction. It works in both cases. So on this side is the same thing. This negation is distributed to the negation of x. So it becomes the negation of x, which cancels out, just becomes x. And then this negation distributes to yi, so yi is negated. But the conjunction has to change to a disjunction. So that's why we end up with a plus here. Okay. Is that okay? Vaguely? Okay. From here to here is distribution. I just multiply out the whole term, which is what you are already familiar with normal arithmetics, right? Please tell me yes. Okay.
Math what?
So I apply the not xi to xi, not yi, and we end up with these two terms. I will distribute this yi to these two terms, and so we end up with yi xi, and then yi not yi. Okay. From here to here, I'm doing some simplification. Not xi is guaranteed to be false, because with this conjunction, one side is the negation of the other side. So one of them has to be false. One of them has to be true, one has to be false. But when you are doing a conjunction, then the false makes the entire thing false. So that's why I put a 0 here, and that's also why I put a 0 here. Is that okay? All right. So the 0 disappears down here, because if you say false or blah blah blah, it really is the same thing as blah blah blah. Okay, so that's why I simplify the false out of the entire thing and just make it look a little bit nicer. Is that okay? All right. And then from there, I start to introduce terms. We use this trick already, yes? Yep. There we go. Okay. So from here to here, I'm just introducing a and true. Okay, blah 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 and true is just blah blah blah. Okay, the truth table can prove that. Okay, and then from here to here, I'm just saying true is the same thing as true or blah 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 or blah blah blah. There's a lot of blah blah blah. Is that okay? Because once you have true and you have disjunction, it's always going to be true. Doesn't matter what you or with true, it's always going to be true. Okay? But by doing this and then do a distribution, now I end up with a whole bunch of terms where the terms can be factored out. So from here to here, I'm just rearranging things. Okay, so they line up better, so we can look at, we can see what we are factoring. So you can see how this term has a TI, this term has a TI as well, this term has a TI, this term has a TI. So I'm factoring the TI from these two terms, I'm factoring the TI from these two terms. But then I realize, hey, there's more that I can factor out, because these two terms, they both have not xi, so I factor out the not xi too. These two terms, they both have yi, so I factor out the yi term as well. Is that okay? So what is left is yi or not yi, which is guaranteed to be true. I have not xi or xi, which is also guaranteed to be true. True and whatever is whatever, so I basically just cancel out and not write the true here, so we end up with this equation here. And when we get to the bottom one, we do one more time of factoring to factor out the TI. So now we have not xi or yi, and then the TI on the outside. Wait, we have seen something like this before in addition.
Yeah.
Only that in addition, there's no exclamation point, right? This one has got some exclamation point. The one in addition doesn't have the exclamation point. Okay. So in this case, let me scroll up a little bit more. So in this case, I'm redefining. Okay, so the key word here is we are redefining, which means the G and the P terms for subtraction are different from the G and P terms for addition. Okay, but they're only slightly different, not really in any major way. So I'm redefining so that GI is not xi, yi. So GI can now go here. I'm redefining PI to be not xi or yi, so that PI can go here. Is that okay? It's just making it look nicer. So with those replacements, okay, by those redefinitions of G and P, now I can express Ti plus 1 as Gi or Pi Ti. Haven't we seen that one before? Almost, this time is exactly. The only difference is before when we were dealing with addition, it was K instead of T. Otherwise, it's identical. Is that okay? All right? So if that structure is preserved, then we can use exactly the same engine to generate the terms for T1, T2, T3, and so on. This is exactly the same. This expansion is exactly the same as what we did with addition. Okay, I can see you guys you have enough of the pine needles already. So we'll take a step back and look at the pine tree. To be more specific, I'm going to show you guys how you can actually make your own subtractor in this case, and it works. Okay, so that you can actually see how all of those terms work together to make a subtractor. And to do that, I'm going to I'm going to use a spreadsheet. So we're going to use Google Drive, and I'm going to go to a folder that will be shared with the class. Just remind me to put that link into the class, so that you guys all have access to this. So cisp310, and there's a shared folder here already. I just have to create the spreadsheet somewhere within the shared folder. And you can see in this folder we have got old exams and stuff like that, but I'll put it under practice. So just remember the subtractor spreadsheet is under practice. And well, I'm still recording, so in case you forget, you can just kind of roll to this particular frame and know exactly where to get it. And then we'll say new and Google Sheet. There we go. Create and share. Yes. Okay. Very good. Okay. So what we'll do is we are going to, is this too small? Should I increase the zoom a little bit?
I can see.
You can see? Okay. The rest of the class? Is anyone feeling that we have to expand a little bit? I'm gonna zoom in just a little bit because when I enter the equation, it's going to be a little bit more difficult to read. Okay, so I'm going to put some real numbers here, actual bits. So I'm going to put 0. Okay, I type on the keyboard, it's just a little bit slow. 0, 1, 1. And I'm going to put a minus sign all the way here. And we'll try 1, 1, 0. Okay. And for those of you who insist, but we need a line under this, we can do that. And we can just go here and look at the, there we go. Okay, so now we have a line under that. This is T0. Okay, T0 can be assumed to be 0, so we'll just assume it to be 0 here. If you want to change that later, that's fine. And we also want to have an underline over here. So we're going to use the same tool to put an underline on this row. Okay, so now we can start to enter some equations. Okay, this is the exclusive OR between the 2 bits ahead of it, on top of it, right? It's the result of subtracting the 0 from the 1. Okay, but instead of putting a 1 here, because we know the result is 1, I'm going to use a formula in the spreadsheet. So this way, when you change the digits, it will automatically recalculate everything. Okay. This is the first time I try to do this, so I'm not really sure whether it has an exclusive OR, okay, or not. Does It is case insensitive, so that should not matter. Okay, so if it doesn't tell me whether there's a function like that, I'm going to say insert, and then we'll insert function. There has to be a way to do it. There we go, insert function, and then we click more so that we can search for exclusive or something to the effect of exclusive OR. Okay, so we want to narrow by, does it have logical? Yes, there we go. So these are the logical stuff that we can do. There's AND, there's false, there's if error, if else, not, or, switch, and true. Unfortunately, it doesn't have exclusive OR. That's okay. We know how to do exclusive OR without exclusive OR, don't we? Mm-hmm. Okay. So without the exclusive OR, I can now do it with an OR. And then the OR is between the end of the negation of this guy and the non-negative version of this one. And then we have the second component of the OR, which is the end of this and the negation of that. Whew. So it tells me it's true. You can always change the format, by the way. You can go to format, because I'm going to force the format of this one to become a number. So you go to Format, and then you go to Number. No, you go to Number, and we want to use a number representation, or we can go for more format. Oh, there we go. We just want the number itself. Oh, it doesn't like that either. Say that one more time.
Maybe number.
Yeah, let's try more formats. Custom number format. And we just want it to be 0. Apply. Nope, doesn't like that. Well,
I think it's conditional formatting. Maybe you've done it before.
Huh?
Go to Format and go to Conditional Formatting.
Conditional formatting.
On the bottom.
Okay.
Never mind.
I mean, it's not that big of a deal.
Well, I can fix it. It's just that I have to put this into if. If this is true, give me 1. Otherwise, give me 0. Okay. There's always a way to do it, right? Okay, so it's going to be the same with these 3. So I'm just going to drag the tab, so it is just copied to the other 2. Okay. 1 exclusive for 1 is 1. Excuse me. 1 exclusive for 0 is 1. 1 exclusive for 1 is 0. 1 exclusive or with 1 is 1. So it does work out so far. So now we have to deal with the borrow bits. Okay, so we'll deal with this borrow bit first. So we have to enter this equation, which is kind of long, because the last operation is an OR, and then inside we have an AND, and then inside that we have a NOT of the first thing. Okay, and the conjunction is with the second thing, and that's done with the AND. Let's see.
And there's an OR.
And there's one more item with the OR, and that item is also an AND itself. And then the first thing is negated, but that first thing is going to be this bit here. It's going to be the Q, right? And then it's ended with the second thing under that, which makes it kind of difficult to enter. I'm just going to say E4 here. So I'm keying in which cell it is ending with. And that is the whole thing that we're ORing. And then we put the close paren here. And now we have, oh, I forgot the conditional to turn it into a 1 or 0. So if that, give me a 1, otherwise give me a 0. There we go. And because the other ones are the same, so we can just kind of drag this. There we go. And now we have this last one. But this one has the same equation as this guy here, so I can just copy and paste. So copy and paste. I should have copied all 3 bits, but it's okay. We can just drag it. Okay. So now we double check, right? They're all 0s and 1s, but does it make sense? Does it work? I can tell it is working already, but we'll double check. 1 minus 0 is a 1, does not contribute a borrow of 1. 1 minus 0 is a 1, does not contribute a borrow of 1. So the next borrow is going to be a 0, because it has, one of these 2 has to contribute a borrow of 1 for the borrow of the next digit to be a 1. 1 minus 1 is a 0, 0 minus 0 is a 0, neither contributes a borrow, so this borrow is a 0. 0 minus 1 is a 1 with a borrow of 1, and then 1 minus 0 is a 1. Seems to work out. If you look at the perspective of the values that the bits are representing, let's check that out too. 0, 1, 1 represents 3. 1, 1, 0 represents 6. Okay? 3 minus 6 is 1, 0, 1 is representing 5. Wait. 3 minus 6 is 5. Hold on, we have a borrow. Right? How much are we borrowing? 1, 2, 4, 8. So the borrow is borrowing 8. So we end up with a value of 5, but we owe 8. What is the net? Negative 3. 3 minus 6 is negative 3. So just by quickly going over the math, it seems to work. But the best part of this spreadsheet is it's alive. You can actually change these bits here. Okay, change this to a 0, change this to a 1, and you can see how the numbers are adjusting all by itself. So this is a good exercise, okay? You can work out something on a piece of paper, give yourself an example of 3-bit minus 3-bit, work it out on a piece of paper, and then go to this spreadsheet and see what the spreadsheet tells you. It should be consistent, okay? So in this case, we have 2 minus 7, and the result is 3, but we have a borrow of 8, okay? So 3 minus 8 is negative 5. 2 minus 7 is also negative 5. So they all check out. Is that okay? So did that address the question? Okay. And I don't want to hear anyone complaining and go like, we're supposed to learn assembly language programming and computer organization, you know, but you're teaching us spreadsheet stuff. Okay, I can see that no one seems to be upset by the use of spreadsheet. A spreadsheet is really just a more complex calculator that is capable of doing more complex calculations for one thing. And then the second thing is it's really good for automation. Okay, and you can use it to analyze everything from your physics and chemistry lab stuff, to even calculus. You can do it to a certain extent. Okay, not a whole lot, but to a certain extent. But for this class, okay, when you're doing calculations like this, a spreadsheet is really helpful because anything that you can do by hand and is mechanical, most of the time you can use a spreadsheet to do it. And later on in this class, you will see how I use a spreadsheet to implement an assembler, which is basically looking at some text and translating the text into actual machine code, and it can be done. I'm going to rename this file because Untitled, it doesn't tell you anything. So I'm going to call this 3x3 subtractor. But it does not make use of the borrow look ahead mechanism. This one does propagate. In other words, if you look very closely or use a very slow computer, when you change these values, you will see the borrow flags changing from right to left. All right?
That'd be a really slow computer for that to happen.
Well, this computer appears to be slow enough for that. So if I put a 1 here, that should change those things. I guess it's a little bit too fast. Just run some games in the background.
Test Crisis 3 in the background.
Or have Windows update itself, then do this. Yeah, that usually will slow down everything to a grinding halt. Yeah, my son was just complaining this afternoon. It's like, when is it going to be done? Because he got his Windows update, and he was trying to get on to play a online game with his friends, and Windows says, nope, we are still updating. We're still updating.
Yeah, do it regularly so it doesn't build up like that.
Well, Microsoft is including a patch today to turn off the Intel patch for the meltdown exploit, because the Intel patch for the meltdown exploit actually doesn't work. So Microsoft has to distribute a patch to turn off another patch because the earlier patch didn't work. So that's kind of interesting. Did you guys update your Windows 10 already today? Yeah, me neither, so that's good. All right, so now I need to go back to the folder itself so that I can show you where to find it. So this is the folder. I'm going to get the link to this whole thing. Okay, so get shareable link. Okay, there we go. And then we go back to the class site itself. Okay, this is Monday, Wednesday. And I'll put it in course information. I'm just adding a link here to the shared folder. So I'm going to insert a URL. And this is the URL. Page name is shared folder. And it will open in a new tab. And there you go. Now you have access to everything in the share folder, which is not just this spreadsheet. There's a lot of stuff in it. Is that okay? Excellent. All right, so we are pretty much done with talking about subtraction because, hey, it turns out subtraction is almost the same thing as addition. In other words, if you have a 3x3 carry look ahead at adder already, all you have to do is to change how you define the P and the G terms. The rest can stay exactly the same. That makes it really easy, don't you think? Yep. Okay. So the next topic is how do we represent negative values, signed representation. All right? Is that okay so far? Okay. So when we talk about signed representation versus unsigned representation, the first thing I need to do is to kind of talk about the number line. Okay? You guys know about the number line. If we are talking about unsigned, okay? So if you're talking about unsigned numbers, then the number line only grows in one direction. Because on one end we have a 0, and then we have 1, 2, 3, blah, 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 and so on. Oh, okay. There we go. Okay, sorry. Okay, so the number line you're familiar with already. If we are talking about integers, then the number line grows in both directions. With 0 here, this is -1, this is 1, this is -2, this is 2, this is +2, and so on this side, and so on the other side. Nothing new, right? Well, as it turns out, in computer science, especially in programming, this is wrong. Integers really should not be represented by a number line. And go like, okay, so how should we represent it? Well, as it turns out, it should be represented by a circle. So instead of thinking of, values on the line, there are values in a circle. And some of you already kind of know, what the major difference is between a line versus a circle. So we'll deal with unsigned first. Okay, so I draw a circle here. How many bits do you want to use? The fewer the bits, the easier it is for me to populate the entire circle. But if you make it like really small, like 1 bit, it is difficult to actually see how the whole thing works. So I would choose between 3 or 4 bits. 4? Okay, let's do 4. The other class chose 3, so it's good. Okay. This is also how I slice pizzas. And I think I messed up somewhere.
What are you slicing pizza for?
Okay. This slice over here and this slice over here. There we go. Okay. That should be 16, notches, right? So let's count. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Ah! 1 too many. I messed up somewhere. Okay. I see where. Okay, so this goes here, this goes here, this goes here. There we go. I'm just looking at the opposite one. Okay? There should be 16 now, which means if you count from 0, you should count up to 15. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm missing one. I skipped one. Okay. I'm just going to stick one here. Oh, when I count, I skip one? Okay. Okay, this means, next time I count, I really should write numbers, right? All right, so we'll write numbers. Okay, so this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. Well, if your integers are represented by 4 bits, it can only represent values from 0 up to 15. What if you add 1 to 15 then?
0.
You get back to 0, exactly. Because to add 1 is to move the hand in a clockwise fashion. So if you're already at 15 and you move 1 notch in a clockwise fashion, it goes back to 0. And that's exactly what's going to happen. Okay? But your integers is 32-bit or 64-bit wide. Does it still have a similar problem? Oh yeah. Okay? If you get to the very largest possible value for an unsigned integer, you add 1 to it, it goes back to 0. Okay? All right. What about subtraction? When you do subtraction, it looks like when we subtract 1, we are moving in a counterclockwise fashion, right? Because I'm just going to pick 1. Okay, let's say you start with 12. Okay? If you subtract 1, it's 11. 11 subtract 1 is 10, and so on. But when you get to 0 and you do subtract 1, what do? You get 15. And when you subtract 1 from 15, you get 14, and so on. So whether you're adding or subtracting, it is still a circle. Okay? Okay. So now we look at the bit representation. So we have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. So those are all the binary numbers, binary representation. Is that okay so far? We just pick one and then we double check. So we're going to pick 10 in base 10. 10 in base 10 is 2 plus 8. Okay, that works out. Okay, so I'm just kind of doing a sanity check on the binary representation. Okay, now this is all you have. Okay, when you look at the binary representation, that's all we can do with all the gates and all the transistors inside the computer. So now the question is, how do we represent -1? Which of these notches is going to represent -1? Which one do you think is natural?
15.
Yep. The bit pattern that so happens to represent 15 can also be representing -1. Okay. So I'm going to use a different color, and hopefully red shows up okay too. Is that okay? The -1? And if you subtract 1 from -1, you get -2, -3, -4, -5, -6, -7, -8. So 1, 0, 0, 0 is a kind of funky one because it can represent 8. It can also represent -8. Is that okay? So some of these bit patterns can represent a positive value. It can also be used to represent a negative value. Is that okay? So now the question is, which one is it representing?
Both.
Well, I got a better question. Okay, let me ask a different question. Why do you care?
I don't want to only want some money. So is it positive money or negative money?
But why do you care whether 1100 is representing 12 or -4? The reason why I ask that question is because if you do the binary subtraction and the binary addition the way we introduced, it doesn't matter. It still works out.
Yeah. -4 to 4 is going to get you 0. -12 to +4 is going to get you 0 as well.
Say that one more time.
-4 plus 4 is going to get you 0, and 12 plus 4 is going to get you 0 as well.
Yep. So it works out whether we look at the binary representation and use the signed interpretation or the unsigned interpretation. Everything that we have talked up to this point still works. The adder works, the subtractor works. Okay? So the question is, why do you care? Or when do you care? So think about your C programs, okay, in C and C++, okay? All the +1, all the auto increment, it doesn't really matter, okay? When you auto increment an unsigned and you auto increment a signed, they work exactly the same way. They go through exactly the same circuitry in the processor. There's no difference whatsoever. When does it make a difference, whether something is signed or unsigned? So addition doesn't care, subtraction doesn't care. Let's not talk about multiplication or division because they do care, but let's not talk about that because to get to that part, we need a much more fundamental operator that you already know in C and C++, and it does care whether something is signed or not. It is comparison. So let's say you have, if, okay, let's see, we go back to black, okay. So let's say you have if x is less than y, then you have a then branch, okay. So the key here is x actually less than y? Now you care, okay. So I'm going to give you an example why you should care in this case. Let's say x has a binary pattern of 1, 1, 1 in base 2. Y has a binary pattern of 0, 0, 0 in base 2, and we're dealing with 3-bit numbers. Okay? So with 3-bit numbers, is 1, 1, 1 less than 0, 0, 0? That becomes the question. Should I perform the then branch, or should I skip over and not perform the then branch? That is the question. So now suddenly you go like, oh, how should we interpret 1, 1, 1? Because 1, 1, 1 can be interpreted unsigned as the value of 7, but it can also be interpreted using the signed interpretation as -1. If 1, 1, 1 represents -1, now 0 is always 0, whether it's signed or not. 0, 0, 0 always represents the value of 0. So now, if x and y are signed, then -1 is in fact less than 0, and you need to perform the then branch. On the other hand, if x and y are unsigned, then 1, 1, 1 is representing 7. 7 is less than 0 is false. You should not perform the then branch. That is the only time that it does actually matter, is when you compare. Is that okay?
So how do we differentiate?
You cannot. So in assembly language programming, in the processor and stuff like that, when you're adding two numbers, you cannot differentiate whether it is supposed to be signed or not, because it doesn't really matter. When you're subtracting, same thing. It goes through the same gates, the same logic, the same structure of the logic gates. It makes no difference whether they are signed or not. But when you compare, then it does matter. Okay? All right. So the next question now is, how do we turn a number? So let's say we're dealing with signed representation. How do we negate it? Okay, in other words, if I give you the representation of 5, how do we get to the representation of -5? And vice versa. How do we do that? Without using the wheel and just count the wheel. Because when you have a 64-bit number, that wheel has a lot of notches on it. Yep. It's called 2's complement. Very good. Okay, so what is 2's complement and how does that work? All right, so new page. There we go. So 2's complement is quite easy. So I'm going to use C2 to mean 2's complement because it's a C1 for 1's complement. So 2's complement of some bit pattern x is really the 1's complement of x plus 1. What is 1's complement? It is also known as bitwise not. And bitwise not in C and C++ is represented by the tilde symbol. Okay, that looks kind of okay. So what does it do? Let's use an example. When you use 2's complement or 1's complement, it is important to understand how many bits we are using. So leading zeros are important and significant when we're dealing with bitwise operations. So let's say we're sticking with 3-bit operations, okay? And we want to check out the 2's complement. I click it again. The 1's complement of 2's complement of 1, 1, 1 in base 2. Okay, so it becomes the 1's complement of 1, 1, 1 in base 2 plus 1, and I said earlier that this is the bitwise NOT of 111 in base 2 plus 1. Bitwise NOT is exactly what the name implies. You go through every single bit and you negate each single bit logically. Okay, so this 0 turns into this one turns into a 0, this one turns into its own 0, and this one turns into its own 0. So 111, if you do a bitwise NOT to it, it becomes 0, 0, 0 in base 2, and then you say plus 1, and that turns out to be 1. So the 2's complement of 111 is 1, which means 111 is representing -1. Because in normal arithmetics, you can use the negation symbol, the minus, to indicate I'm flipping the sign of this thing. So now, I don't have enough time to really illustrate it, but the claim is, 2's complement on a binary number is doing exactly the same thing as an arithmetic negation. Okay? If you do a C2 on 0, 0, 1, it should give you 1, 1, 1. So I think we got enough time to do just that. Okay, so we'll go ahead and do that. So we'll do a 2's complement of 0, 0, 1 in base 2. That becomes the 1's complement of 0, 0, 1 in base 2 plus 1, which also means this is bitwise NOT of 0, 0, 1 in base 2 plus 1. Bitwise NOT, once again, is flipping each bit, individual bit, to its opposite. So the 1 turns into a 0, the 0 turns into a 1, the 0 turns into a 1. So we have 1, 1, 0 plus 1, which turns out to be 1, 1, 1 in base 2. So if I claim that 2's complement is negation, then this actually works out. The negation of 1 is 1, 1, 1. The negation of 1, 1, 1 is 1. That works out. Is that okay? So we're running out of time at this point, so you please read the module, on signed numbers, because this is all coming from that module. Okay? And we do have lab activity tonight, which is the construction or the partial construction of a 3x3 carry look ahead adder. If you have done it already by yourself, still you have to go through the exercise. Because this one makes use of the multi-bit gates, and it does make the design a little bit simpler and easier to understand. Yep.
Can you scroll up a little bit? A little bit?
Is that
The wheel?
huh? To the wheel, okay. You mean this one?
Yeah.
Okay.
Oh yeah.
See you in a few.
Yep.
You know what? It's not working. I got
Not even.
Are you good? Okay. Okay. So we're gonna turn this off. Let it sleep.